Okay, so let's move on. So last class, right, I was talking about log. It stands for Laplacian of the Gaussian, and we had shown that it's actually a bandpass filter. We'll kind of revisit this today quickly down the line, not now. And there's another thing, right? So what to say? So there is actually an approximation that you can do of the log, which is through a dog. Okay, and dog stands for a difference of Gaussian. There is also another dog which is a derivative of the Gaussian. Okay, but this is a difference of the Gaussian, difference of two Gaussians. Okay, it's possible, and there is a theoretical explanation for this, which will not go through. But many times, right, you will find that a simpler approximation to log comes through a dog, which is a difference of Gaussians. Of course, they have to have a sort of a relative spread. So difference of two Gaussians will look like some g of xy comma sigma minus some g of xy comma k sigma or something. Okay, where this k has to be chosen appropriately, and such a difference also tends to approximate a log. Okay, and for computational reasons, people typically prefer a dog. In fact, when we go through some of those feature detectors, right, we'll see how this dog comes into play more. It's actually an approximation to the scale normalized log and so on. I'll talk about it when we do feature detectors. Okay, just a quick point regarding the Gaussian, because in your assignment, right, the lab 2, there is some filter implementation and so on. Okay, so I just wanted to kind of quickly tell you how to do a Gaussian. So for example, right, if you think about it, I mean, right, you might wonder that a Gaussian is sort of infinite in extent and so on. So you can do some quick approximations. So for example, right, if you have a Gaussian which is g of m comma n, a discrete Gaussian especially, right. So let's say you've got like 1 by 2 pi sigma square e raised to power minus m square plus n square by 2 sigma square. Okay, so when you do a discretization, now first of all, right, what should be the support of this Gaussian? So what is normally done is, right, if you take a Gaussian, whether in 1D or 2D, doesn't matter. You know that of course this has an area 1, right? And if you take 3 sigma, if you go like 3 sigma on either side, right, then you would have covered approximately 99% of the area, right? So only about 1% lies outside. And therefore, typically what is done is you take like a 3 sigma on either side, so minus 3 sigma to say plus 3 sigma, and that sort of, right, covers more or less the extent of a Gaussian, because you cannot have a filter that goes right very high different dimension. It doesn't make sense also. So what is typically done is you take so suppose somebody specifies a sigma for a Gaussian. This is one way to approximate. There are other approximations, but the simplest I thought is this. So what you can do is somebody gives you a sigma, then you can do a seal of 6 sigma plus 1 such that it's an odd number. Okay, typically filters are odd, right, so that the center is clear. I mean, if you take a 4 by 4 filter, it's not even clear where the center is, right, and you don't lose anything. You can just you can actually construct a Gaussian such that right, I mean, it extends to an odd number, the size. And then what you should do is you should compute GMN for all the way from m comma n, right, going from going from minus 3 sigma to 3 sigma or whatever, right. If this seal comes out to be, let's say, a 13 cross 13, right, then this in the m and n will go from, say, minus 6 to 6, right. That will be the extent. If it is 5 cross 5, then it will go from, right, minus 2 to 2, whatever, right. Depending upon that, your m and n will take a certain range. You calculate GMN from this equation, but that if you sum up that GMN, right, that need not kind of sum to 1, because this is a discrete approximation. Therefore, you simply do a sum normalization, right. I mean, that is the simplest way to normalize. So you can create a G dash of Mn, which will be equal to what? If you wanted GMN to sum to 1, what would you do? Exactly, right. So simply do a sum normalization of GMN, and that will give you a G dash Mn, which you can use an approximation for this one Gaussian. Okay, so this is one of the things that you should be just aware of, because a uniform filter is easy. I mean, I give you 5 cross 5, you will simply say 1 by 25 everywhere. But if I say create a Gaussian with a certain sigma, right, then you might wonder what should be the spatial extent of the filter and so on. And therefore, this is one of those simple approximations that you can do. And this one, right, and a Gaussian, is not just something, right, that plays a role in terms of you know, a weighted smoothing, right. So one of the nice characteristics about a Gaussian is that when you are sitting at a place, right, it tends to give more weightage to that pixel than to the neighbors. Whereas a uniform filter, if you think about it, it doesn't care about, you know, right, it just gives equal weightage to whatever is around it. Whereas you will typically believe that let me give more weightage to where I am, right, to the pixel I know that I want to average, and I should give more weight to that, and then I should probably, you know, decrease my weightage as I go outside, right. That's what a Gaussian does. So it's a kind of a weighted averaging, right, as opposed to a uniform filter, which is like, you know, uniform weights all over. And this control that you have, right, the sigma gives you a nice control, and this as there is a whole theory called the scale space theory, okay, that is based upon a Gaussian. Okay, we will talk about some of that. Okay, so there is something called the scale space theory, where the scale is associated with sigma, right, and then you start examining an image at various scales, and the idea is that, you know, certain things pop up, you know, right, depending upon how you kind of, right, how you run through your sigmas and so on. That is something that we will see later, but just wanted to tell you that Gaussian, this is not the end of the story for the Gaussian, right, and as we go forward you will keep encountering Gaussian in again and again. Then of course, you know, I talked about horizontal and vertical edge filters, right, something very simple that we talked about last time. And the smoothing filter, okay, is a Gaussian, so it's kind of a weighted smoothing. And yeah, let me just show you some examples, right, just to kind of give you an idea, and then we will go to the, okay, this I will come to later. Okay, so see a box filter, when you smooth, right, this is how you will get, because this is like, you know, smoothing everything right equally. And this is again, right, another kind of a box filter result. Again, right, another, whereas if you use a Gaussian, right, then it doesn't all, I'll skip, I already talked about all this. Then you see that, right, it's not exactly the same as what you get with an averaging filter. Of course, it doesn't mean that we do all, right, everything with a Gaussian and all. I mean, these days there are these are all called local means, okay, in the sense that you are averaging locally. Okay, now there are filters that are called non-local means. That means you don't have to necessarily look around. You can actually go scout for values elsewhere. We will not be talking about those kind of filters, right, in this course. Then this is a uniform filter again, and then, right, you can see the effect of sigma here. I think so it's like this. So as you go down, right, you are kind of increasing the smoothing. So around increasing the smoothness. So if you take any one, okay, if I tap here, you can see that, right? If you take any one, and then if you go down, right, it's like, you know, no smoothing, then sigma equal to 1. So that will be like, what will be the spatial extent? Sigma equal to 1, 7 cross 7. Right, 6 sigma plus 1, right. So that will be like a 7 cross 7 filter, which you will build up. Sigma equal to 2, what will be the spatial extent? Okay, so you can see that, you know, as you go down, right, I mean, you get the blurring effect to be higher and higher, and then you take a Gaussian filtering, right, then depending upon what value of sigma you choose, right, you can end up blurring things heavily, and sometimes this could be used for, let's say, privacy and so on, but not always. Okay, there are various reasons why you want to do smoothing. And then a Gaussian versus box filtering, right, this hopefully brings out some of those advantages that let's say, right, a Gaussian has. So you can see that, you know, the bricks are, I think the bricks are actually right, I mean, if you look at the top one, top right, that has a better sort of filtering, right, in the sense that you can see that the central weighting is actually better there compared to something like a, you know, uniform filter down. Then this is a gradient kind of thing. So what do you think is the second one? So that is the original image, is the first one, and what is coming in the middle? So what kind of a filter is that? What kind of edges are you seeing there? Vertical, right? So therefore it's a kind of, you know, a vertical filter, and then the other one is actually trying to pick up all the horizontal edges. So it's like a horizontal filter. We will also talk about orientation of edges and so on down the line. This is again another example of Sobel. So again, right, you have a brick, and then depending upon which filter you apply, you can pick up horizontal or kind of vertical edges. And these edges are some things that we saw in CNNs also, right? Okay, this let's kind of skip this for the time being. This and all we will skip, and then yeah. So well, I'll kind of come to this when we do, you know, edge detection. A derivative of Gaussian, this again I'll come to later. Okay, yeah. I think at this point of time, right, let me go back to what I was talking, and okay. So the other thing, right, that I wanted. Sorry, yeah.
Sir, in the g of m comma n,
Huh.
so you have written e power minus m square plus n square.
Well, this is all kind of say zero centered. The one that I have put is actually centered about the zero, and normally, right, that's the way you look at it. I mean, when you have a Gaussian, no. I mean, so you take the central thing to be kind of say 0, comma 0, and then you can extend.
But in the kernel, so the center is at 0 comma 0.
Center is always at 0, comma 0. The center is always 0, comma 0. Even in a uniform filter, if you have minus 3 to 3, I mean, you'll always take it to be minus 3 to 3, and the center is always kind of say treated as 0. So it's like, it's like in that filtering operation, right? If you look at it, you have like GMN, and then let's say is equal to some summation FMN, H of m minus n, or whatever. So that H of m minus n, or you write it as HMN F of, so that HMN is always 0 centered. So it's like you go from you go over the spatial extent of the filter, and that's about 0, comma 0 always. Yeah, so here we don't have that. You're probably thinking in terms of mean and things like that, right? I mean, zero mean. I mean, if you want to think about it, but this is not statistical in that sense. This is like a deterministic filter, right? And just as one more thing, right? See, right, based upon what you have seen, right? There is something called unsharp masking, okay, which is what do you think it does, right? Because always, right, people get this is a very strange term. Unsharp masking. What do you think it must be doing? Unsharp masking. By just the look of this word, right? What do you think it must be? It must be doing. Is it like sharpening, or is it like smoothing? Smoothing, right? No, it's actually sharpening. It's like unsharp. That means you are smoothing, masking. That means you are masking the blur. Right, you have to think about it like that. I don't know who coined this word. They could have made it very simple, but that's what it's called. Okay, it's a very standard thing. And the way this works is as follows, right? So you have I, suppose you have an image I, right? Then the unsharp masking looks like this. So the original I plus a constant times whatever A or K or whatever, I minus I blurred. And this guy is something like 0.2 and between 0.2 and 0.7. Again, there's nothing sacred about that. So it's like this, right? So you take, so again a Gaussian comes into play here, or any kind of smoothness filter. So you blur I to get your IB, and then you do I minus IB. That's like a detail that you're getting, right? That's like a high frequency information, and that you kind of you scale it, right, by some number, and then the scaled high frequency detail you add to the original image, right? That's why it's called like unsharp masking. So it's actually sharpening effectively. I mean, you're trying to bring out a detail, and that's what actually was there in the first one, right? When if you saw, you noticed the very first one, right? That the very first thing, right? So what does blurring remove? So if you see, right, this is the original Lena, then there is a smooth Lena, here it's just a weighted average, this uniform filter, then this is a detail. So if you subtract, right, I minus IB, that is the detail, and then you multiply it with some constant, this detail, and then you add it to the original, right? Then you end up actually sharpening the image. So this operation is called unsharp masking.
I minus I blur will be a sharpened version.
No, it's not a sharpened version of the image. That will just contain details, high frequency detail, edges and so on.
Okay.
That won't be a sharpened image itself. That will be like I think. And then you add it to the original. No, yeah, it's like this, right? See, when you do a blurring, right, and so it's like this. If I gave you, let's say, right, a low pass filter, and if I said that I wanted a high pass filter out of it, how would you arrive at that? Suppose I had a filter already which can do a low pass filtering operation, and I want a high pass filter, right? What would that be? No. I'm saying just a filter. Okay. Let's not even worry about an image. Let's say I have a filter. This can do a low pass filtering operation. But I want from this filter, I want to arrive at a high pass filter. Be very careful. It's in the spatial domain, right? Okay, right, in time domain, for example, if you wish, or a filter in the spatial domain. 2D filter I have. This, if I run around, I can smooth, correct? Now I want a high pass filter. I have this. I should be able to get a high pass filter from this, right? How would I do that? No, but then in spatial domain, I'm asking the spatial domain, right? What would that be? Yeah, all pass, yeah. What will that be? what would it do? A delta Mn minus this. Would that not be? Would that not be the one? Right? You see, in the Fourier domain, if you think about it, you need something like a 1 all through minus the low pass, that will give you the high pass. I mean, right, like this, no? I mean, you have a low pass, I want a high pass, right? So what will I do? I can do this 1 minus this, that will give me a high pass. What is the 1 for in the spatial domain? It's a delta, right? So in the spatial domain, you do delta, which will be like just a delta at the center. Everywhere it's 0. Minus this, right? That's what you will do. That's exactly what's happening here. No, I minus IB, if you look at it, IB is what? IB is simply I convolved with some low pass filter. So you can pull the I out, you will have well, I mean, right, in this case, because it's actually a convolution, right, it will be a delta minus the low pass filter. That's what it is. So it's not like you're losing anything, right? I mean, you are getting high frequency information, details. Okay, so unsharp masking, right, so it works like that. And okay, now, right, this actually the other application, right, of these filters is actually in this one, denoising. Okay, like I said, again, right, simple applications. Okay, these are not very complicated. I mean, if you look at the most recent literature and all, it's way beyond what we are talking. But I think it's important to at least know these things, so that when you read that, you can associate, you can relate to what we have done. So denoising, the simplest case, right, that you can think about is actually AWGN. So what you have is an image, right, with which has been affected by, let's say, a Gaussian noise, okay, and let's say with a kind of with the same variance everywhere, and you want to be able to reduce the effect of noise, right. Now there is I mean, you would have all seen that people typically will take a filter and then you do a spatial averaging, but that comes out of actually I'll just run through this very fast. Okay, so it's like this. I mean, if I gave you multiple frames, right, this actually happens in your cameras. See, if I gave you multiple frames of the same scene quickly taken, right, so that there is no motion, nothing happens, I just grab 50 frames quickly. Can I sort of do something to mitigate the noise? What would you do? You will take the average of all of them, right, because the scene hasn't changed. I've got multiple shots of the same scene very quickly taken. So you would do an average of that, right, and what will be the effective variance then of the noise? You see, originally, let's say each one has a sigma square noise, right, in it. I've taken L number of images, I've averaged them. What will be the new variance? Sigma square by n by L, whatever, right. So this is the right number of frames. So right, that comes out of this, right. So you have like GMN. And this is actually done in your cameras. Okay, so GMN is, let's say, okay, let me take the ith frame, I of f of m comma n, plus let's say eta I, which is the noise of m comma n, right. This is what you have as a model. Now what you are saying is you are trying to get an estimate of at any m comma n, right. This is valid at any m comma n. You will just say, right, I will just do an average of 1 by L, let's say summation Gi of m comma n, I running from 1 to L. This is what you said, right, you will do. Now, right, this being noisy, right, so it means like you're having an estimator of f, right. That's what this f hat is like, an estimator of f. So one of the things that you look for is what is the mean value of this f hat. What should it ideally be? F itself, right, fmn, and that you can easily show, because this is 0 mean, right. So this we have taken to be 0 mean with some sigma square, let's say, noise. And therefore, right, if you just run it through the summation above, you will get that this is equal to fmn, which is good. Such an estimator is called unbiased, right. This is unbiased. And then what you can do is, if you look at the variance, right, how would you like the variance to be? Should be low, right. I mean, about this value, because you are already like on the average you are getting to the correct value, and the variance about this should be as less as possible, right. And therefore, if you look at variance of f hat of mn, right, that will be whatever, right. So that will be expectation, what is it, f hat mn minus this guy, right. What is it, the mu f, right, which is actually fmn, okay, the mean, right, square. And this, if you do, right, it's very straightforward to show this. You just substitute it for f hat of mn, which is 1 by L, this one Gi, and then if you do this, right, you will end up with exactly what you said, sigma square n by L. Okay, that's what you will get to be the effective variance, and such an estimator is called a consistent estimator. Okay, so right, that is the most nice thing that you can get as an estimator, something that's unbiased and something which is also consistent, in the sense that the more observations you add, the effective variance of the noise goes down. But then in reality, right, you cannot denoise like this, right. I mean, suppose normally you will have just one image, you may not have 20 images with with you. Therefore, what you do is you do what is called a local averaging, and then the essence of that comes from here. It's like saying that, see here, one of the assumptions which you made was that these were all aligned, right, in a sense. So when you take just one image and then you want to do some kind of noise mitigation, then what you do is you take a filter and then you apply it locally, and this interpretation is that the other pixels are like the other frames, the information coming from the other frames. It's like, but then you have no other go now. You can only locally average. You don't have information from other frames. You have only one frame. But this averaging notion actually comes from there. And the idea is that the idea is that locally, right, these intensities will be like similar, and therefore right, they are all affected by, let's say, independent noise, right, each one, and therefore when you average them, you should effectively get a variance that's actually less than the variance affecting a single pixel, right. So the idea exactly goes like that, but in reality, right, it may not work out that well, because these intensities need not always be the same. They are, right, you can't assume that they are the same, and therefore it affects your edge preserving capability, because it could be that right there lies an edge, right, and then when you sum up, right, all this assumption that you are making is all gone, and therefore when you do that, you will get a smearing effect, which is kind of annoying when you see that. Because such things happen, that's why you go for filters that are far more superior than this, okay. But this was what was done, right, originally, and then there are several other improved versions of that, okay. So which is what you can do if you had an AWGN kind of noise. Then the other kind of noise, right, I am talking about this because in your lab too, right, you have these things, okay, as part of the assignment. So you have to actually incorporate these filters and so on. The other one, right, that you can do is a salt pepper noise, okay. So instead of the AWGN, the other one, like I said, right, something that is sprinkled and then which is kind of signal independent typically. And there, right, what you use is actually a median filter, okay. Kind of median filter is very simple. So what you do is, suppose you choose a size for the filter, let's say I choose some like 3 cross 3, then what you do is in the image, right, wherever you are, okay, if you take a 3 cross 3 window, then you actually take all those intensity values, put them in an ascending order, or you can put them in whatever a descending order, and then you simply pick the median value, and then you replace the central guy with that. See, in all of this, you will put every value in a kind of a new grid, okay. You don't put it back there, okay. You understand, right? When you do a convolution, you always copy it into a new array. I mean, you don't put it back in the same place, otherwise it will affect the next result, right, because it's all spatially related, no. Okay, so you need to, so that and all I'm assuming right. So you kind of copy it into a new array, and where you will have, and then in a median filter, the assumption is that if there is an outlier, right, it will go either to this end or to that end, right. It will go either to the max or the min, and therefore when you take the median, right, it should not be there, right. And there are various higher versions of this. You can also do a weighted median, just like you have a Gaussian which is doing a weighting, right. You also have what is called a weighted median, where what you do is if you have a median filter, let's say, right, I mean, you just have to specify the size, because in a median there is nothing like weighting or something, but that weight you can bring in by saying by kind of specifying another kernel, where you say that where you kind of put some numbers, okay. What these numbers mean is that each of these should repeat that many times when you do the right before you take the median, right. So it's like you're emphasizing certain guys more. So you say that because if you were to take a simple median, you just have that value appearing once. But suppose I write 2, that means you have to put that value twice. And then if I say 3, that means the next value, whatever is sitting here, should be copied thrice, and then you sort. Right. So when you do that sorting, right, depending upon which one is repeating more, right, it will have an influence on the final result. So that's also called a weighted median. Now all these are typically, see, the other one that we talked about, which is the Gaussian, right. There I said that, or whatever, right, a box filter, it was easy to come up with a high pass filter, right, because it's all a convolution operation, whereas median is actually a nonlinear filter, okay. This operation is you all know, right, median itself is not really a linear operation. So therefore, right, if I asked you how would you do a high pass filter with a median, the low pass thing, it's clear fairly, right, that if I wanted to pull out noise or mitigate noise, I can do something like this and walk away. But if I asked you, right, can I do a high pass filter? In the sense that one simple explanation could be that if I had uniform values everywhere, right, okay, this we keep talking about, right, you have a wall or something where, let's say, intensities are all the same, and if I apply a median filter there, of course, if all the intensities are the same, you will again get back the same value itself, right. But if I said that the output should be 0, because now it's a kind of a plain wall, right, it's a homogeneous region, I need high pass filtering. What would a high pass filter have done? if you are doing a convolution and all, that would have simply picked up a 0, right. We saw, no, the sum of the weights for a gradient filter is 0, or a Laplacian for that matter is 0. So, anytime you apply it on a place that is like, you know, all same values, it will always output a 0. How will I make a median filter output as act like a high pass filter? Huh? No, I want directly a filter. Well, you are saying I'll first, you know, create a low pass filter version, but that's again, right, that's all assuming that there is a convolutional model underneath. What you are saying, right, is still banking on some kind of a convolutional model. I mean, it's like I minus IB, you know, right. So, if you rewrite it, you are coming back to convolution kind of a model, but actually this is a nonlinear filter. I mean, implicit, I mean, you are not explicit, but implicitly you are implying a convolution kind of operation. How do you do that? Anyway, right, I'm going to leave this to you as an exercise, right. Think about it. I might ask it in the exam also. Okay, I want you guys to think about it. Okay, so that let's leave you guys to have some fun. Okay, now this okay, now all this was in the spatial domain, right, and exactly